Hi, it's time to talk about velocity time graphs, okay? And I'm going to do that via an example. So this is for M1, the mechanics course, part of A-level, and here's a typical velocity time graph scenario. So the diagram shows a velocity time graph of the motion of a cyclist moving on a straight road for a period of 45 seconds, okay? So this is typically what a velocity time graph might look like. What I'm going to do is I'm going to talk you through what's happening at each stage of the journey. Okay, so you need to be able to do this as well. You need to be able to draw one of these given information or be able to interpret what's going on from the actual graph. So what we'll do is just split it up. So between 0 and 10 seconds, the first 10 seconds of motion, what's happened? The cyclist is speeding up, increasing velocity from 0 to 15 meters per second. Okay, we can actually work out what the acceleration is because that's called an acceleration. When someone is speeding up, it's called an acceleration. Okay. Now you should be aware that the acceleration formula can be calculated using change in velocity over change in time. So I'm using the small delta symbol there to represent changing because it's quicker. Flash back to I G to C or flash forward to M2, pick your choice, okay? But you don't need to know this for M1. You can actually write that as dV dt, okay? So a bit of a calculus thing there. The deltas can actually originally dV dt when you take all the limits and so on. I'm not going to get into that. Okay, but essentially what you do is you find the gradient, aren't you? Okay, because the change in velocity is going to be 15, and it's positive 15 because it's increasing from 0 to 15. So let's write that down. And the change in time is 10, so it's over 10 seconds. Increase in velocity, 15 meters per second over 10 seconds. That's 1.5. Okay, and we write that as 1.5 meters per second squared. Okay, like that, or m stroke s squared. Okay, meters per second squared. So that's the acceleration. That's what happened in the first part of the journey. You would write something along the lines of cyclist is increasing in velocity from 0 to 15 meters per second, and acceleration 1.5 meters per second squared for the first 10 seconds. Okay, that's that bit done. And then next, well, the cyclist is now not changing velocity at all. It's a flat line. Zero gradient, we say the acceleration is 0, neither speeding up nor slowing down. And so for the next 20 seconds, travelling at constant velocity, we say, of 15 meters per second. And then finally, they're slowing down. That's called a deceleration. Okay, but we still use this as an acceleration formula. Okay, and the way we work it out is we consider that there's a change in that it's decreasing in velocity. So that's negative 15. You can see actually that the gradient is negative, it's sloping downwards. So if you were considering this, you'd have a negative gradient. And that's taking place over a 15-second time period. So that's negative 1. So the acceleration, I'm going to write it like this time. The acceleration is negative 1. Okay, that's slowing down at a rate of 1 meter per second squared. We say a deceleration of 1. Slowing down of 1 meter per second squared by an acceleration A of negative 1 meter per second squared. Okay, that's what's going on in the first 45 seconds. And well, I've answered that question as well, haven't I? Find the acceleration each part of the journey. It's this, just to confirm: 1.5, 0, and negative 1. Okay. Right next, find the total distance travelled by the cyclist in the 45 seconds. Well, I no longer need that anymore. Total distance travelled. Okay. Well, let's just consider this bit here first of all, because I'm just going to show you how a velocity time graph can be used to find the distance travelled. Let's work out the distance travelled between t equals 10 and t equals 30. Now, considering the cyclist is moving at 15 meters per second for 20 seconds, you can see that you just could do 15 multiplied by 20, aren't you? Okay? So for each second, they move 15 meters. And they're doing it for 20 seconds, so 15 by 20. Can you see that that is just working out the area of this rectangle? Okay, the area of this rectangle represents that total distance that's been travelled. Okay, and in fact, the area underneath any velocity time graph will give you the total distance travelled, which is rather a cool thing. Okay, in terms of this bit here, well, because they're moving with constant acceleration, okay, what you can do is you can look at what the distance would be if they'd been travelling at a constant speed of 15 meters per second. So if they were moving at 15 meters per second throughout, they'd do a distance of 150. But because it's a constant acceleration, in other words, starting at 0 and at 15 meters per second, the average distance travelled, averaging it out, would be half of that, okay? Because you have to realise they've not travelled anything at 0, and then when they reach 15, you just do the multiplication. That is, of course, the area of the triangle. Okay, that's just a demonstration, not a proof, a demonstration of the area underneath one of these velocity time graphs gives you the total distance travelled. Now you may as well finish it off, then you can do the area of this bit, so that's just another triangle, and that's just be half times base times by height, half by 15 by 15, okay, and that can give you the total distance travelled. So that's going to be half of 225, which is 112.5, that's going to be some 75, and that's going to be 300. Yeah, and add that up, and you get a total of 487.5. Okay, so just check that. Yeah, 487.5 meters. Now, had you known that at the beginning, there's a better way you could actually work it out. Let me just reset that there. Consider this as a trapezium. Just work out the area of a trapezium. Trapezium formula, of course, is 1/2 a plus b multiplied by the height, where a and b are the two parallel parts of the trapezium. Okay? Get used to doing it that way because it's so much quicker. Okay? Most graphs do look like this shape. It's a trapezoidal shape. Okay? It's a wonderful word, isn't it? Trapezoidal. Okay? Thanks to the Americans for coining that one. And what I'm going to do is I'm just going to work it out that way, okay? So this bit here is going to be 20. Just put that in brackets. And then the B, this bit here is going to be 45. And then the height is going to be from here to here, which is 15. Okay? And if you work out half times 20 plus 45, okay, you'll get the same answer, 487.5 meters. Okay, and that's our total distance travelled by the cyclist. Okay, so before I go on to the rest of it, two really important points there. Okay, that is that the acceleration is denoted by the gradient, it can be positive, 0, or negative, and the area underneath a velocity time graph gives you the distance travelled. Okay, before we go into the rest, I'm just going to pause and show you this screen. I'm going to step away in case you want to take a screenshot of that or something, because it essentially covers what I've just said, the important bits, okay? And I've included the area of the trapezium there as well, all right? Moving back, I'm just going to take you through another part which I've created for this question. Find the average speed for the journey. Well, can you see that the total distance travelled is 487.5 metres, total time was 45 seconds, so average speed is distance travelled divided by time taken. So it should be 487.5 divided by 45, and you should get an answer of 10 5/8, 10.8 metres per second. You can, in the mechanics exam, generally round to 3 significant figures, okay, or 2 significant figures. I generally put the exact answer and then a rounded answer. It just covers all bases, okay. And then there's another part. Here we go. Last bit, I'll just put that on there because it's a nice extra question to do. The cyclist passes a bus stop after 240 metres from his starting point. After how many seconds does he pass the bus stop? Maybe pause the video and just work it out yourself if you want. Okay, and then unpause the video and just see how you get on. I don't know if you did that or not, but I'm going to go through it now. Okay, this is one of the wonders of watching these videos, because you can pause and I can just continue. So let's clear that. So, cyclist passes a bus stop after 240 metres from his starting point. Okay. Well, do you remember that this bit here we worked out was 75 metres? And you can do it again if you wish. Okay, so half times 15 times by 10 is 75 metres. Okay. And do you remember we worked out this bit in here was 20 multiplied by 15, which is 300 metres. Now the 240 metres must be in this bit. Okay, that's crucial, because you've got to know roughly where on the graph that actually happens. So I'm just going to notionally put it there. Okay, I'm going to put it there. That's the 240 metres. Okay, so basically the cyclist is passing the bus stop when they're already at their maximum velocity, should we call it, when they're not accelerating anymore, when they're travelling at a constant speed. All right. What I'm going to do is I'm going to work out what the difference between 240 metres and 75 is. Okay, so 240 subtract 75, that's 165 metres. Okay, so that means is after getting up to the maximum speed, maximum velocity, the cyclist has got to travel another 165 metres before they get up to the bus stop, before they pass the bus stop. Okay, and what we need to do is just equate this area here with the 165 metres. Okay, and the 165 metres is going to be whatever time this is. I'm going to call it capital T for time, multiplied by the velocity they're travelling at. Okay, 15t. Or alternatively, you can look at it this way: 165 metres at 15 metres per second. So work out the time taken, do 165 divided by 15. Okay? So 165 divided by 15, that's just 11. Okay? So it'll take the cyclist 11 seconds, it's an S there for seconds, to pass the bus stop after they reach their maximum velocity. Okay, so altogether, including the 10, okay, you've got 10 plus 11, that's going to be 21 seconds. So after how many seconds do you pass the bus stop? 21 seconds after the starting point. Okay, and that is a lovely summary actually of velocity time graphs and how they work. Okay, I'm hoping you found that useful. Okay, and yeah, some more videos coming up soon. See you again.